In question 6, we've got a car moving along a straight horizontal road. At time t is 0, the velocity of the car is capital U meters per second. We are told that the car then accelerates with a constant acceleration of a meters per square second for capital T seconds. The car is traveling a distance of capital D meters during these capital T seconds. This is the velocity time graph for the motion of the car, and we need to use the graph to show that capital D is ut plus a half at squared. No credit will be given for answers which use any of the Suvat formulae provided in the formula booklet. Well, I will start with the fact that the distance covered is given by the area under the velocity time graph. So going on the graph here, we've got this area here giving me the distance. So what I can do is I can split it into a rectangle and a triangle. We know that the gradient here is simply the acceleration, so the gradient is a, and I'm gonna call the height of the triangle h. So I can use the fact that the gradient is rise over run, so the rise is h and the run is capital T. This means that a is equal to h over capital T, and therefore a capital T is equal to h. Now the distance will be given by the area of the rectangle plus the area of the triangle. The rectangle is simply capital T times capital U. So we've got ut for the rectangle, and for the triangle it's going to be base times height over 2. Well, the base is capital T, the height is h, so base times height over 2, which leads to capital D being ut plus t times at over 2, which of course simplifies to d being ut plus a half at squared as required. In question 7, we've got a car moving along a straight horizontal road with constant acceleration. Now we've got 3 points A, B, and C in that order on the road, with AB being 22 meters and BC being 104 meters. Now we are told that the car takes 2 seconds to travel from A to B and another 4 seconds to go from B to C, and we need to find the acceleration of the car and the speed of the car as it passes through A. I will draw a straight line representing the journey. We've got A, B, C along the journey here. I'm gonna add the time points. So at A, T is 0, at B, T is 2, and at C, T is 6. I will also add the distances of 22 meters and 104 meters respectively. I'm gonna call the velocity at A to be U meters per second, and I'll be using Suvat equations because we're experiencing constant acceleration throughout the journey. So I'll be using S is ut plus a half at squared, and I will start by considering the journey from A to B. We know that the distance covered is 22, and this is equal to 2 times U plus a half times the acceleration, which is unknown, times 2 squared. This gives me 22 is equal to 2u plus 2a. I will divide throughout by 2 to get 11 is equal to u plus a. And I will then proceed by considering the journey from A to C. Now from A to C, we have covered a total distance of 22 plus 104 meters, which is 126 meters. The initial velocity is still u, so it's gonna be u times the time 6 plus a half times the acceleration of A times the time of 6 raised to the power of 2. So we're looking at 126 being equal to 6u plus 18a. I will divide throughout by 6 to get 21 is equal to u plus 3a. So we're essentially dealing with simultaneous equations in u and a. I'm gonna write the first equation we obtained just below the second equation we just obtained. So 11 is u plus a, and I can deduct 1 from the other to get 10 is equal to 2a, and therefore 5 is the acceleration. And I will proceed in substituting into 11 is u plus a to find u. So we're looking at 11 is equal to u plus the a, which is 5, so 6 is u, and therefore we conclude that the acceleration is 5 meters per square second, and the initial velocity u is 6 meters per second. In question 8, we've got a bird leaving its nest at time t is 0 for a short flight along a straight line. The bird then returns to the nest. Now the bird is modeled as a particle moving in a straight horizontal line. The distance as meters of the bird from its nest at time t seconds is given by this expression here, where t varies between 0 and 10, and we need to start off by explaining the restriction that t has to be between 0 and 10. So starting with the expression for s in terms of t, we notice that we can factor out the t squared. So we're looking at t squared over 10, and within the brackets we've got t squared minus 20t plus 100. So this further factorizes into t squared over 10 times t minus 10 all raised to the power of 2. Now, since we are modeling the journey of the bird as it leaves the nest and then returning to the nest, let's investigate for the values of t when s is 0, so when the bird is at the nest. So if I set s to be 0, this means we're looking at t squared over 10 times t minus 10 raised to the power of 2 being equal to 0, which of course means that either t is 0 or t minus 10 is equal to 0. So we've got t is 0 or t is equal to 10. And therefore we conclude that since the bird is back at the nest at t is 10, we need t to be between 0 and 10 inclusive. In part B, we need to find the distance of the bird from the nest when the bird first comes to instantaneous rest. So starting with the expression for s, I will expand. The idea is to differentiate to find an expression for the velocity and then find the time at which the bird is at rest. So let's start by expanding. We're looking at s is equal to t to the power of 4 over 10 minus 2t cubed plus 10t squared. We know that the velocity v is given by ds dt, the derivative of displacement with respect to time. So this is 4t to the power of 3 over 10 minus 6t squared plus 20t. We know that being at rest simply means that v is 0. So at rest means that v is 0. And therefore we're looking at 4t to the power of 3 over 10 minus 6t squared plus 20t is equal to 0. Now the 4 with the 10 simplified to leave me with the 2 in the numerator and the 5 in the denominator. I will start by multiplying throughout by 5 to get rid of the denominators. This takes me to 2t cubed minus 30t squared plus 100t is equal to 0. And I can proceed by dividing throughout by 2 to get t cubed minus 15t squared plus 50t is equal to 0. I can factor out the t, taking me to t brackets t squared minus 15t plus 50 is equal to 0, which further factorizes into t brackets t minus 10 times t minus 5 being equal to 0. So we've got t is 0, or alternatively we've got t minus 10 is equal to 0, or t minus 5 is equal to 0. So a total of 3 solutions: t is 0, t is 10, or t is equal to 5. However, since the question is asking for the distance when the bird first comes to instantaneous rest, we can see that the bird first comes to instantaneous rest at t is 5. So I need to find the distance when t is 5. So I simply have to say that when t is equal to 5, we've got that s is equal to 1 over 10 times 5 to the power of 4 minus 20 times 5 to the power of 3 plus 100 times 5 squared. Now if I plug this on the calculator, we get that s is 62.5 meters. In question 9, a small ball capital A of mass 2.5 kilograms is held at rest on a rough horizontal table. Now the ball is attached to one end of a string. The string is passing over a pulley P, which is fixed at the edge of the table. The other end of the string is attached to a small ball B of mass 1.5 kilograms hanging freely vertically below P and with B at a height of 1 meter above horizontal floor as shown in the diagram here. Now the system is released from rest with the string taut. The resistance to the motion of A from the rough table is modeled as having a constant magnitude of 12.7 Newton, and ball B reaches the floor before ball A reaches the pulley. Now we are modeling the balls as particles, the string as being light and inextensible, and the pulley as being small and smooth. And in part A, we are asked to write down an equation of motion for A and then an equation of motion for B. Now, as always, I will start by adding all the forces acting here. So considering A is feeling the tension to the right and is feeling the friction to the left, opposing motion of 12.7 newtons. And we know that A will accelerate to the right, whereas B here is feeling its weight of 1.5 g. It's feeling the tension which is acting upwards, and B will be accelerating downwards. So if we start by considering A, we've got forces acting to the right minus forces acting to the left is mass times acceleration. So we're looking at T minus 12.7 is equal to the mass of 2.5 times A. And if we consider B, we've got forces acting downwards minus forces acting upwards is mass times acceleration, which means we've got 1.5 g minus T is equal to 1.5 A. In part B, we're asked to hence find the acceleration of B. So starting with the two equations we just obtained in capital T and A, I can simply add them up to eliminate the capital T. So we're looking at 1.5 g, and I'm using g to be 9.8, minus the 12.7 is equal to 4a. Now the left hand side gives me a result of 2, so 2 is equal to 4a, and if I divide both sides by 4, I get 0.5 to be the value of a. Now using the model, we need to find the time it takes from release for B to reach the floor. So going back to the diagram here, we know that B was initially at rest. It will experience a constant acceleration of 0.5. It will cover a distance of 1 meter. So I can use Suvad equations here. We've got that S is ut plus a half at squared. The distance covered is a meter, it's 1. So ut is 0 times t plus a half times the acceleration of 0.5 times t squared. This gives me 1 is t squared over 4, which means that 4 is equal to t squared, and therefore t is equal to 2. This is the time it takes from release for B to reach the floor. Now we are told that it was found that it actually took 2.3 seconds for B to reach the floor, and I need to use this information to comment on the appropriateness of using the model to find the time it takes ball B to reach the floor, justifying the answer, and then suggest one improvement that could be made in the model. Now remember that in part C we found a time of 2 seconds, so the first thing I need to say is that 2 is not close to 2.3, hence the model is not appropriate. Now how do I justify my answer? I could say that ball B took longer because the model did not include air resistance. In reality, we've got air resistance, which is slowing the ball down, so it takes a longer time to cover the distance of the 1 meter. And then to suggest one improvement that could be made in the model, I could suggest taking into account the mass, weight of the string, or take into account the dimensions of the ball.